Marcus! 1-5. Coming. Oh, this one. Was there a particular part? So you got the second line, though. So I did have somebody come and ask me about this. One thing is where you're putting the squared when you type in the in on the calculator. So I'm just going to squeeze it in over here on the right. I'll use green because it'll totally stand out from the rest. It's cosine x squared, but the question is, where is that squared? Is it on the x? Is it on the cosine? Where is it? Because then it will depend on how you type it in on the calculator. That squared is only next to the x, so it is only on the x. That is one of the reasons why we have the notation. If we want it on the cosine, we actually put the squared on the cosine. But that's not it, so I'm going to cross it out. So when you're typing it in on the calculator, this is how you're going to want to do it. You're going to put just the x squared in the parentheses. And on the calculator, because you know when you type in cosine, how it automatically puts that first parenthesis in? I am sorry, I'm squeezing this in. Let's change it to blue. If you type this in on the calculator, so it forces the parenthesis open. So you put the x, you close the parenthesis, you put the squared there. On the calculator, this actually means this. So it's, if you put the exponent outside the parentheses, then your calculator is going to interpret it wrong. So that could be what was throwing you off. But if you got the second line and just didn't get the actual answer, that was it. Any other questions? By the way, let me just I'll show you one thing that you could do, because this one, I don't know how many of you guys actually did this one, or if you're like, I'll just set it up and like look at the answer and see if I got it right. And, yeah, because you didn't want to type this in on the calculator. Because even though I showed you that way of like doing y1 of square root of pi over 2 over 4, it's still kind of a pain to type in on your calculator. There is something you can do to make it a little bit easier. And especially, it's kind of nice because they gave us 0. So actually, since I have my calculator open, let me go ahead and go over there real quick. I'll show you another trick you can do. Maybe. There we go. Oh, hang on. I have to restart my calculator. Sometimes it freezes. Boop, boop. 12 your thumbs, wait for it to open. Okay. So, I don't have the problem up anymore, but you guys have it on your paper. When you calculate delta x is the problem, because delta x itself is root pi over 2 all over 4. That's a pain to type in. So just type it in once and save it to a variable. So I'm going to do second square root. It's even more of a pain because I don't have a touch screen. Is it pi over 4? No, it's pi over 2. And then all over 4. So that's delta x. I'm going to store it. And I'm going to store it in, I can store it into any variable I want. Oh, and by the way, I store this button right here above the on button. So you click that and you see the little arrow. Choose whatever variable you want. I want to make this super easy. And I don't need to use x elsewhere in the problem. So because I have this quick, easy button to press to get x, I'm just going to store it into x. So there's that. Now I never have to type that in again. So now when I type it in, the formula is delta x over 2 times, and I know I don't have the function into y1, so I'm not going to get the same thing, but I'll just do the first one, or the first two, just so you can see. So y1, now the first one is just y1 of 0, so I have that. but then plus 2 bars y1 of delta x. Oops, I need parentheses. And you just keep going with it now. And actually, because of the 0, this wasn't very interesting. The next one, 2, well, the next one was adding 2 delta x's, so I can actually just say 2x and keep going with it and blah, blah, blah. And it just makes typing it in a lot easier. So little things you can do to help making the typing in. And also you're less likely to make a silly mistake, because if you try to keep track of all those parentheses with the root pi over 4 over 2, whatever it was, I don't know. Anyway, so that's that. Any questions about that? Okay. By the way, actually, I'm going to just end it here. You know how I said, oh, I know I don't have it entered in Y1? Let's say like this was, I really wanted the answer, and I'm like, crap. I just got this far in the problem, and I forgot to put it into Y1. It's okay. Finish it up. Pretend I finished typing all of it in. Just hit enter. Then go back into here. Enter your function in. And then all you got to do is hit enter again. It's going to recalculate that expression based on the new value for y1. So don't think like, oh crap, I'm going to have to type it all in again. It's not that bad, actually. Any questions? All right. Hopefully you guys were using your homework or your calculator during your homework. I really do. This semester, I want you to use your calculator more and more. Get really comfortable with it. Play around with it. See all the stuff it can do. Because it's going to help you on the test. It'll help speed things up. Any other questions on the homework? All right, well, let me have your homework then. And we do have a reality check-ish. I'm not going to collect it. I'm going to let you guys just keep it. But it'll be over log sand trapezoidal rule. And actually, I'll just go ahead and I'm going to pause this. But there's number 1. Any questions on that? Anybody want more time looking at it? Very exciting stuff, huh? Wait until you see number 2. Well, man, actually I can fit them both in. There's 2 and 3. Yay! Yeah. Oh. There it is. Any questions over any of them? So 2 and 3 were DNA. DNA. Anybody ever do one of those DNA tests? They're kind of fun. You did it? Oh, really? Did you learn anything about... I've thought about doing it for my dog. Oh. Alright. I actually, one year I bought the test for me, my brother, and sister, so we could all do them. Because I've always wondered, I mean, if you look at me and my brother and sister, we don't look anything alike, I don't think. So I always wondered, are we really blood related? And it turns out we are. I wanted a scandal. There wasn't one. People always ask me, like, you did? You did that? What happens if it turns out you guys aren't blood related? Wouldn't that change things? I'm like, no. Why would it? My brother and sister actually thought it was funny. All right. Well, with that said, actually what I want to do, I do want to go back and look at that, that free response question we were looking at last time. So go ahead and pull it out. And keep going over there. I don't want to go over there. I'm going to get mine out here as well. So I'm just pulling up last time's notes. I had a brain fart that was kind of stinky, so I want to fix it. And I also, we probably won't have time. I kind of wish we had time to look at D. Because D has some stuff I could show you on the calculator. But we'll come back. We'll look at D. But I want to look at B and C. I want to revisit those. And comparing those, we'll actually get something across. So we already did A. Here was B. And I'm going to make some adjustments here. So not only if you have the free response, but if you have your notes also, because we're going to make some changes to the notes. And I apologize, but we're going to fix it. Okay, so right down here, I'm just going to jump down to here, just to refresh our memory. Remember that part B had us approximate this expression using trapezoidal sum, and the part that in yellow, trapezoidal sum only approximates definite integrals. So the yellow is only from the trapezoidal sum, but then you have to take that answer and divide by 8. But I have to fix a few things. First of all, I have a funny line there. I don't know what that is. We had that, remember the panic at the end where I thought I left out per hour and we put it in, but notice I don't have it in anymore. Actually, take the per hour back out. I don't know if you remember, we added, it was hundreds of entries, and we said per hour. Oh, I see where that line was. That was part of the P. That's weird. Hundreds of entries per hour deposited, blah, blah. Actually, let's take the P out of there. I mean, technically, I guess it would work, but it's actually a broader statement than that. It really is, actually, probably, I should say, I should have the words on average. That's really what we want. I'm going to add that here. Approximately, on average, there are blah, 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 blah. So anytime I look at the number of entries in the box, I should see, on average, that number. It's not per hour, it's at any time. The other thing, though, that I actually want to fix is this part right here. Because that's actually not correct. And that's what this is where I really had the brain fart on Monday, and that was what was throwing everything off. Trying to put a meaning towards this integral is kind of hard. And I'm actually, I still don't have a good way to phrase the meaning of it. But I can't remember, was it no, because we were doing, anyway, yeah, we didn't have a chance to look at that. I'm trying to remember what I did in each class. Let's look at the units that are going on here. So this part right here, this integral, it's a definite integral. So we know definite integrals represent area under a curve. Now they didn't actually tell us what the function E of t is, so I have no idea what that function looks like. But I'll just make something up. But that definite integral does represent the area under this curve. Now, if you think of the units that are involved here, then, on the x-axis is hours, and on the y-axis is entries. We know it's hundreds of entries. I'm just going to write entries. So the area, if you think of length times width, the units that are here are just entries times hours. Length times width. Entries times hours. So trying to put into words, I mean, what would that mean then? At least I can't think of what the words are that would describe what the meaning behind that integral is. But as soon as we also multiply by this fraction, and remember the fraction, the units for this fraction, it's 1 over hours. because 8 minus 0 represented the hours. So now when you multiply, if we put these together, 1 over hours times entries times hours cancels out, and you get entries. So this whole entire expression, the units on this whole entire expression, is entries in hundreds. So, and then we also know that this is the average value of the function, and the function in this case is E of t, which represents the number of entries being in the box. So on average, the number of entries is 10.687. So the integral by itself doesn't really have the important meaning, but as soon as we multiply by this fraction, then it has meaning, and we're talking average number of entries in the box. Does that make sense? What might help it make more sense is let's look at C and kind of compare. All right, if this integral by itself doesn't represent the number of entries, what does? So let's look at part C real quick together, and then we'll go on to today's lesson. So I'll come back and see if there's still questions, because you may just trying to chew on that. So part C. Now we didn't have a chance to look at part C at all. You guys hopefully at least read it. But let's remind ourselves, because we've had a couple of days. So part C says, at 8 p.m., volunteers began to process the entries. They processed the entries at a rate modeled by the function p, where p of t equals, and they give you this polynomial. According to the model, how many entries had not yet been processed by midnight? So let's chew on this a little bit. Let's kind of write down what it's given us. Let's kind of summarize this. So they say p of t is the number, it's the rate at which the entries are being processed. So p of t is a rate at which entries are processed between 8 p.m. and midnight. Which is t between 8 and 12. And again, it's hundreds. Hundreds of entries. So the question is, how many entries had not been processed by midnight? Question. How many entries are still unprocessed at midnight? So any questions, just what's going on in this scenario? Does it make sense? So between time equals 0 and time equals 8, people kept putting entries in the box. That was in the table at the top of the question. Then they accepted no more entries at 8 p.m. And then the workers started processing them. They started, I guess, tallying up the entries. But they only worked so fast, and by midnight there were still some that were left undone. So how do we figure out how many are left undone? Well, what we really need to do is this. Let's go back up to the table for a second. So people kept putting entries in the box, and at 8 p.m. when they cut it off, there were 2,300 entries in the box. Now I'm going to stop saying hundreds of entries. We know it's in hundreds of entries. Let's just say there's 23 left in the box. So now they're going to start processing these guys. So starting with 2,300 entries, between 8 and 12, they processed some of those. How many are left unprocessed? So we have to figure out between 8 and 12, how many entries were they able to process? And then we just subtract from 23 and we get it. So what we're really going to do is we're going to take the number of entries at the end, which is at t equals 8. We're going to take that and subtract the number of entries processed between 8 and 12. That's really what we have to do. Does that make sense? Now, this they give us. We know that that's 23. That's from the table. Now the question is, how do we figure out the total number of entries processed? And this is where we use the fact that we have P of t. P of t is the rate. Oh, if it's a rate, what should you automatically be thinking of? It's a derivative. So P of t represents a derivative. The derivative of what? Well, it's the derivative of whatever the function is that represents the number of entries processed. If P of t is the rate at which the entries were processed, then P of t is the derivative of the function that represents the number of entries being processed. Does that make sense? So if we want to find the function, we want to undo a derivative, and what action in calculus undoes a derivative? Integrals! This is where we're going to do the integral of a rate, and we're going to go from 8 to 12, because that's the hours that we want to figure out how many entries were being processed. But this integral now, because this integral is an integral of the rate at which entries are processed. Can't spell the word processed. Processed. This equals the total number of entries. So this represents the number of entries. And in this case, because the limits were 8 and 12, this is the number of entries processed between 8 and 12. And then you could use your calculator, because this is a calculator question, and you get the answer. Turns out the answer is a nice whole number, I guess, huh? So the answer is 7. But then we know it's in hundreds of entries. So the difference between part B and part C, we're taking the integral of a rate. If you're doing the integral of a rate, you're left with a meaningful thing, which is the total number of stuff. In this case, the total number of entries. Part B wasn't really the integral of a rate, it was the integral of a function, so putting a meaning in this context is a little harder. But any questions about that? Does that make sense? I can't tell. You guys aren't giving me any indication if it makes sense or not. On a scale of it makes sense to makes no sense to anywhere in between. Okay, actually I'm going to take this because I was hoping for at least halfway, and I don't see anybody below halfway. So for our first time through, I'm actually happy with this. Rena, yeah. So this is, you kind of like reason through the wording. So in order to answer the question, we need to do these boxes, which means we really needed to find something to represent the total number of entries processed, but all we had was the rate at which the entries were processed. If we could just undo the rate, we'd have the number of entries. And to undo a rate, it's undoing a derivative. That tells you the integral. Any other questions? Okay, we can put that problem away. Let's look at today's notes. Much more exciting. We're going to go back to natural logs. Yay! I know that's what you guys were thinking. Right? Oh, yeah. I can, but it's just going to take more time than I want to right now. So I'm sorry. I'm not going to take the time out of class. We'll come back and look at stuff like that, though. So don't worry. Because it is a good one. And there's some good stuff on the calculator that we can do with that. All right, we're going to start chapter 5 now. So this is section 5.1, which is natural logs. And specifically, we're going to look at differentiation today. Differentiation. So I'm just going to give you, like we've talked in the past about what natural logs are, base E, all that good stuff. But here's a calculus definition of the natural log of x. And I'll go through a few things to show you that this definition actually works. It's not going to be conclusive that this definition works, so you are going to have to take my word for it that it works. But the definition, the calculus definition of the natural log is this. The natural log function can be represented by a definite integral. The integral from 1 to x of 1 over t dt. And I know that may seem a little weird, but let's see how these actually do compare. So I'm going to call this guy y1, and I'm going to call the right-hand side y2. And let's just compare y1 equals the natural log of x to y2 equals the integral of 1 over x, 1 to x of 1 over t dt. So if I got y1 equals natural log of x, we know a graph for that. A graph for this, remember it has a vertical asymptote at the y-axis. And it's this increasing function that crosses the x-axis at 1, 0. So this graph has some characteristics. So that means that natural log of x has some characteristics. First of all, if x equals 1, the natural log of 1, what is the natural log of 1? I think I heard it. Yeah, it's 0. Because remember, if you do the around the world, remember the invisible base is e. E to the power of 0 is 1. Because anything to the power of 0 is 1. If x is a positive value, x is greater than 1, so if we're over here to the right of 1 on the x-axis, we can see that natural log is also positive. I don't want to say equals then. The natural log is positive, which means y1 is positive. And actually, I'll scroll up here. And then if x is less than 1, and I should be more specific and say between 0 and 1, because x can't be a negative value. So if x is between 0 and 1, then we can see that the natural log is now negative. The natural log of x is negative. It turns out this integral will have these exact same characteristics to it. And we can see that if we do a graph. So this graph, remember, was just the graph of y equals natural log of x. To look at the definite integral, I'm actually going to graph y equals 1 over x. Actually, I'll say 1 over t. We'll make this a t-axis. And y equals 1 over t would be, whoops, I hit the wrong thing, would be this hyperbola here. So we can look at these three same characteristics. If x equals 1, what is happening to the definite integral? And we can see that from looking at the graph. Well, actually, for this particular one, we don't even need to look at the graph. If x equals 1, that definite integral is going from 1 to 1 of 1 over t dt. But automatically, because the limits are the same, what's the answer to this integral? 0. Which is exactly what we got over here. If x is greater than 1, then the integral, I'm going to actually, this is running into it, then the integral from 1 to x of 1 over t dt. So we have to think about this a little bit. I'm going to just put 1 right there on our graph. Remember, this integral would represent the area under the curve 1 over x. And so if x is greater than 1, we're looking at the area starting from 1 and going to the right. But all that area is above the x-axis, and we're going to the right. We're adding on the area. It's positive area. So this integral is positive, which is what we expected. When x is greater than 1, we expected a positive answer. If these two things are equal, if the natural log of x really is that definite integral, it should have been a positive area. This one we have to think about. If x is between 0 and 1, so now we're looking at this area to the left of x equals 1, which is above the x-axis. So you might be thinking, well, wait a minute, that's still positive area. That's not going to give us a negative answer. But my limits are going backwards now. The bottom limit is bigger than the upper limit. The lower limit is bigger than the upper. When your limits go backwards like that, it actually changes the sign of your area. So what was positive area is actually negative area. And we still get a negative answer. And so it works. If you look at other things, if you actually had a way to compare actual values, you would see the natural log of x really will be exactly the same thing as this integral. Yes, Rena? I heard, shouldn't the limits on the last one be, but then I couldn't hear you. No, because I'm still just saying, I'm defining x to be anything between 0 and 1, so I still want an x here. Any questions about that? So, this definition up here, whoops, really does work. Let's put it on a cloud. It deserves a cloud. Oops, I cut off the one. Woo! There we go. So what can we do with this cloud? Well, it's actually a pretty powerful cloud But don't worry, it's not going to be a rainstorm. It's going to give us rainbows and unicorns. It's been kind of cool, actually. All that rain that we had last month. Did you see all the rainbows that kept popping up? They were pretty cool. There were lots of rainbows. I don't remember actually seeing that many rainbows over and over again. That was kind of fun. All right, so going back to this thing. I'm just rewriting the definition down again. So I wonder if we could use this to perhaps find the derivative of the natural log. And the answer is, oh, you betcha. So starting with this definition, I'm going to take the derivative with respect to x of both sides. We're going to do dx of the natural log of x. And we're going to do dx of the integral from 1 to x of 1 over t dt. Now on the left-hand side, I don't know what the derivative of the natural log of x is, so I can't really do anything with it except write the derivative of the natural log of x again. But you should be able to tell me what the right-hand side is. Anybody know what the derivative of the integral from 1 to x of 1 over t dt is? Perhaps using a theorem from last unit? A pretty important theorem, like a fundamental theorem, Trey? Is it 1 over what? It's 1 over x. Remember the fundamental theorem in calculus? I'll put it over here. FTC Part 2. Remember, that's the one that said if you're taking the derivative of an integral from a constant to x of f of t dt, that's just f of x. It's exactly what we have going here. We're taking the derivative from a constant to x of a function of t. It just becomes a function of x. That's it! Holy crap! And then, what if it's not the natural log of x? What if it's the natural log of a function of x? Then it's chain rule. It's 1 over, this time we have u of x, but then chain rule says you have to multiply by the derivative of what's inside. Remember chain rule? It's been a while. And there we go. Now we have the derivative of the natural log. Here's how you'll typically see it, though. So this is, anyway, I'll write it down. Derivatives of the natural log function. So the derivative of the natural log of x, it's just 1 over the argument. If you have a function instead, when you look at tables of integrals and tables of derivatives, they typically don't write out u of x. They actually, you'll often just see natural log of u. They just say u instead of u of x. But it's 1 over u of x times the derivative of u of x. And this is how you will typically see it written. Yeah. Derivativatives. So the derivativatives, I don't even know how to say it. Save it. Oh, I could just do that. Am I there? Thanks. Derivatives. Yeah, that'll work. Thank you. What? I know. Derivativatives. Is that a hand up, David? Yeah. Because of the fundamental theorem of calculus, and because I'm using this along with this definition. So if I take the derivative of both sides, I get here. And the derivative of this definite integral is 1 over x. Because the FTC part 2 says, if you have a derivative of an integral from a constant to x, the derivative of the integral of a constant to x, of a function of t, it just becomes a function of x. So this function of t, 1 over t, becomes a function of x, 1 over x. Yes?
The part where you think like the properties are the same, doesn't that work for any log function?
No, it won't. And we'll actually do that next unit. We'll look at other bases. It's close, but we'll have to do a little extra. Any other questions? All right, so let's just practice this. Let's see. There's not much to this, actually. It's once you get used to it, it's pretty easy. But then this is actually going to help us with some of those tougher derivatives that we had last unit. So let's take a look. First of all, I want you guys to try doing this one. I'll give you it's your first one, so it's kind of simple, but you also haven't seen it. Anyway, try this one. Try finding the derivative. And I'm just going to make this. Find the derivatives. So part A. Try the natural log of 2x. Just try that one and see what you get. I'll only give about a minute, and then we'll look at it. Anybody think they got it? If you were thinking about this, like if you got an answer and then stopped and thought about it, you may have thought, wait, that seems weird. Because there is kind of something weird until you think about it, and then it's like, oh, yeah. Yeah. The answer is 1 over x. But wait, whoa, wait a minute. The reason why that seems weird is because it's the derivative of just the natural log of x that's 1 over x. How does the natural log of 2x also have the same derivative? I don't know why I put equals right there. That should be y prime. How are we getting the same derivative down here that we got up? It's bizarre, isn't it? But not if you think about it. First of all, if you're like, I don't even know how we got 1 over x. I was going to do the work over here. So we're starting with this guy. And now I don't know, there's a couple of different ways Marcus might have gotten this. Marcus, can you walk us through how you did it? First way? You mean that you did have 2 ways of doing this? This is weird. Okay, so we'll come back to him. He said chain rule. And remember, chain rule and the derivative of the natural log is 1 over the argument times the derivative of the argument. And then 2 over 2x, that really is just 1 over x. So any questions on this way? The 2 on the top? That's the derivative of the bottom. So this is like this is the argument, this is our u. This is the derivative of the argument u prime. Once you do tonight's homework, if you don't have it by the end of today, you'll have like, oh yeah, Natural log. Anytime you're doing the derivative of the natural log, argument on the bottom, derivative on the top. Marcus, you said that the first way or one way, anyway, you implied that you had another way of looking at this. What's this other way? Oh, right. Remember your properties of natural logs? You can actually use the product property here and expand it. And then the natural log of 2 is just a constant. What's the derivative of a constant? 0. And then the derivative of that is just 1 over x. So that's why you actually do end up getting the same thing. And then if you're like, well, wait, should I expand it? Do I have to expand it first? It's up to you. You're going to get the same thing. All this works together. That's why math is so beautiful. It's like this big puzzle piece where all the pieces fit together in multiple ways. It's kind of neat. Anyway, there's that one. Any questions about that? Let me have you guys think about another one then. Does anybody still need any of this? Okay. Let's line this up. All right, part B. Y equals the natural log of x cubed. Find that derivative. Anybody get an answer to this one? Joshua. 3 over x it is. And you can't always do them 2 ways, but this is another one. You could have done it 2 different ways. You could have just argument on the bottom, derivative of the argument on the top. But then the x squareds cancel out and you get 3 over x. Or, if you expanded it using the properties of logs, then you still get 3 over x. Oh my God! It's magic! I can tell you guys are excited. Calm down. Any questions? Let's try another one. Okay, try this one. Part C. Y equals... I'm going to cube the whole entire natural log. I watched my very first episode of Jeopardy last night with the new guy, Ken Jennings. I hadn't actually watched him yet. He's pretty good. That was good. Anybody watch Jeopardy on a regular basis, or occasionally at least? It's like, I love it how they have Jeopardy followed by Wheel of Fortune, which are both awesome games, but like Jeopardy It's where you've got to have like the super nerds, the brainiacs, the people with this random trivial knowledge that they... And then you go to Wheel of Fortune, and it's like, oh, phew! It's all light and happy, and yeah, anyway. It's kind of weird, isn't it? All right, anybody have an answer to this one? This one gets a little harder now. It's just, I mean, it's not, but it is. It's been a while since we've done derivatives, right? We kept focusing on integrals, so... Yeah, Trey. Why, yes, it is. Whoop. There you go. So you got to do chain rule on this one. So remember, you got a composition of functions, and unfortunately, there's no other way to do this. We can't use any of our properties of logs with this, because that exponent is not on the argument; it's on the whole thing. So take the derivative of the outside function, which is cubed. So you got to multiply by the exponent and decrease the exponent by 1. So keep the inside the same, but then you multiply by the derivative of the inside. And there you go. Any questions? Okay, I have just 2 more problems left. Try this one. Y equals the natural log of x cubed plus 3 all over x times the square root of x plus 7. Just think about that for a moment. I'll give you like 20, 30 seconds to think about it, but then I'm going to interrupt you and we'll talk. Does anybody have a strategy that they would recommend for solving this? Supra? Expanding it. Yes. Do not. It would work, but oh my God. Do not do this without expanding it, because think about what you would have to do. If you didn't expand it, the derivative of a natural log is 1 over the argument times the derivative of the argument. 1 over the argument wouldn't be that bad. We just flip that fraction. But then you'd have to take the derivative of that argument. We have quotient, product, and chain rule all happening in this problem if you tried to take the derivative as is. That would suck. Now, I made you guys do it last time, because sometimes you got to do it, but we don't have to do it. Expand this thing first, and then take the derivative. You'll see it's so much easier. I'll let you guys finish now. You don't have to combine them all into one fraction, by the way. Leave them separate. It's fine. Anybody have the answer? Or an answer that they want to try? And I was like, oh, no. All right, I'll put it up here. Oh, sorry, Marcus. I just saw your hand. So if you expand it, you should get here. And then it's each term, 1 over the argument times the derivative of the argument. 1 over the argument times the derivative of the argument. Minus, that's just 1 over xn. And this guy, we do have the 1/2, so I put the 2 in the denominator already. But then 1 over the argument times the derivative of the argument. Thank goodness for those properties of logs, huh? This is one of the big reasons why we have those properties. Any questions there? So really nice when you can expand, right? One more problem. Anybody still need this though? Okay. While people are writing that down, here's our last problem. Just noodle on this. We'll actually do this one together. Y equals x cubed times the square root of x squared plus 1 all over 5x plus 17. And be careful how you write that. I purposely put the multiplication sign and like spaced it out because if you put x cubed right next to the square root, it can start to be a little unclear. Like, wait a minute. Is that cubed on the x or is that a cube root? I don't know. Anyway, very obvious if you do it like that, or even parentheses can help. Just be careful. It's not cube root. It's x cubed times the square root. Right. Anybody still need the old problem? Do you have a question? Or? Oh, that's an excellent question. So David's wondering, is this supposed to be the natural log? And no, it's not. Would be a lot easier with the natural log, though, wouldn't it? Because if we had the natural log, we could do what we did in Part D. We could expand it. We don't have a natural log there. So guess what? We can't expand. So it's a product and a quotient and a chain rule all wrapped up into one. Marcus? Yeah, there's a trick. It would be a lot easier with that natural log, wouldn't it? So let's put it in there. This is called logarithmic differentiation. So it would be oh my goodness, come back here. It would be a lot easier with that natural log. So I'm going to put a natural log in there. But wait a minute. You may be thinking, you can't do that. And you're right, I can't do this. But what I can do, as long as I take the natural log of both sides, I'm okay. So logarithmic differentiation, you take the log of both sides. It's still an equivalent equation now. And now we can go ahead and expand. And you may be wondering, well, how are we going to do this? And don't worry, you'll see. So if I expand this thing, I get 3 natural log x plus 1/2 natural log x squared plus 1 minus the natural log of 5x plus 17. I haven't taken the derivative yet. All I did was I took the natural log of both sides, so that way I could expand the right. So any questions just about that? So now we go ahead and take the derivative of both sides. Now the right-hand side's not going to be so bad. Time-consuming writing it all out, but we know how to do that. Natural log of y, though, how do we take the derivative of that with respect to x? Trey? That's exactly it. Now we go back to implicit differentiation. But also think about our property or our rule for differentiating natural log. Remember, I keep saying 1 over the argument times the derivative of the argument. 1 over the argument. So anyway, our argument is y. Derivative is 1 over y times the derivative of y. And this is implicit differentiation. So I can still get a dy dx out of this. And then I take the derivative of the right-hand side and get 3 over x. I have the 1/2, so I'll put the 2 on the bottom. And it's 1 over the argument times the derivative of the argument minus 1 over the argument times the derivative of the argument. So just take a look at that. Let me know if you have any questions, just how I got here. All right. Now for our notes, I'm going to write it out in more steps, but we could get right to our final answer all in terms of x pretty easily. First of all, with this middle fraction, we can see the 2's are going to cancel, so I'll do that in the next step. But all I have to do to get the dy dx by itself, to get the derivative by itself, is just multiply both sides by y. And if you're like, well, do we have to put our answer back in terms of x? Yeah, but we know what y equals, right up there. So we could, like I said, for our notes, oh man, I think I can squeeze this without making it too squeezed. You could just jump right to your final answer, but just so the notes we see it. So I'm going to take this thing, canceling out that 2 on the middle term. We just multiply both sides by y. And if you have to put your answer all in terms of x, that's okay. Because we know that y equals the stuff on top in blue. Dun, dun, dun. And there's our final answer, all in terms of x. Ta-da! A lot better than doing the product, quotient, and chain rule all in one than trying to keep track of it all. I don't want to do it. We'd have complex fractions. Oh my god. Oh, it would be awful. Anyway, there you go. Any questions about that? So remember, I'll go back here if you're still writing it, but remember, if you have the natural log, go ahead and expand it. Make life easier on yourself. And if you don't have it, but wish you did, well, go ahead, put it in. Just don't forget, if you put it on one side, you got to put it on the other. And then you do logarithmic differentiation. Any questions? All right.